Good day to you all. Welcome to the third lecture of tanker operation lecture series. Today we will discuss about flammable range and flammability diagram. At some point of the lecture, we will try to construct a flammability diagram for a specific cargo like methanol. Let's begin. What is flammable range? The flammable range, also known as the explosive range, refers to the range of concentration of a flammable vapor or gas in air that can ignite or explode when exposed to an ignition source such as spark or flame. So that means each of the cargo has got a range to support combustion or to support explosion in a specific atmosphere. That cargo concentration should be within that range, then only the cargo will support flame, right? This range is normally defined by two limits. The first one we call it lower flammable limit or lower explosive limit, or the second one we call it upper flammable limit or upper explosive limit. What is lower flammable limit and upper explosive limit? We'll get the definition now. So here actually we can see that there are different cargo is given. For different cargo we have got different lower flammable limit and upper flammable limit. These values you'll get it on material safety data sheet, right? So what is the definition of lower flammable limit? The lower flammable limit is the minimum concentration of a vapor or gas in air expressed as a percentage by volume, right, at which combustion can occur. So it is the minimum percentage of that gas or hydrocarbon which can support combustion, and it is always expressed in percentage by volume, right? Below this limit the mixture is too lean. That means it is not enough to ignite, right? We know that to support combustion we require three important elements. One is oxygen, another one is fuel, and the third one is heat or flame, right? So here if the cargo's concentration is below the lower flammable limit, then it will be too less to support the combustion, and the fuel will be too less, right? Whereas upper flammable limit or upper explosive limit is the maximum concentration of vapor or gas in air at which the combustion can occur, right? And above this limit the mixture is too rich, right? That means there is too much fuel and not enough oxygen to support the combustion, right? So obviously we know that for to support the combustion we require oxygen, and as per ISGOT or as per the industry, to sustain a flame we require at least 11% of oxygen, right? Anyway, when we'll be discussing the flammable diagram it will be much more clear, right? Let us see what is a flammability diagram. So here on the right hand side you can see a flammability diagram. Here we have got a flammable envelope. Here we can see that overreach. Here the cargo concentration is too much, and therefore the oxygen is very less, and therefore there will be no combustion. And here is the cargo concentration is too less to support combustion, right? And here below 11%. So here actually it is the non-flammable zone, right, where actually the combustion will not occur, right? To support combustion actually the cargo concentration or hydrocarbon concentration should be within this limit, right? And it is different for different cargo, right? So this flammable diagram is a graphical representation of the flammable limits of a substance in air, right? And it indicates the concentration of a substance in air needed to ignite it and the concentration at which it becomes too rich to burn, right? And obviously we have told you that the diagram itself varies for different flammable gases, right? Let us see what are the key features of this flammability diagram. In the axis it shows the oxygen concentration. It is always percentage by volume. right? So here is 0%, 4%, 8%, 12% in that way, up to 21%, right? In the y-axis, it shows the hydrocarbon vapor percentage in mixture, right? And here we get the lower flammable limit and upper flammable limit, right? And the most important thing, from this flammability diagram we get the flammable envelope. So that flammable envelope indicates the range of hydrocarbon concentration and oxygen level within which a gas air mixture can ignite and sustain combustion, right? So this, if you want to sustain a combustion, so obviously the air and gas mixture has to be within that flammable envelope, right? So in the next following slide we'll try to develop this flammable envelope flammability diagram. Let us take a cargo. The cargo is methanol, right? So once you're going to load the cargo, obviously you'll get this MSDS or material safety data sheet from the terminal or from your charterer, and here in the physical and chemical properties you'll get all the important parameters of that cargo. So here we have got the upper flammable limit for methanol is 36.5%, right? We make it round, we take it 36%, and the lower flammable limit is 6%, right? So let us draw a flammability diagram for methanol, right? So for that, what you need to do, you need to take a graph paper. In the graph paper, in the x-axis you'll have the oxygen percentage in mixture, percentage by volume, right? And on the y-axis you will have hydrocarbon vapor percentage in mixture, percentage by volume, right? So we already know that for methanol the lower flammable limit is 6% and upper flammable limit is 36%, right? So we take a I want you to draw this graph or flammable diagram with me. So you need to take a pencil, you need to take a ruler, and let's draw it, right? So what you need to do, you just need to point different point in the oxygen percentage. So 2%, then you have got 4%, then you have got 6%, then you have got 10%. Then in that way we need to point different point in the x axis. Then we just give the percentage, right? Here is 2%, 4%, 6%, 8%, 10%. Then we give 11%. Why 11%? Because this is a vital value of oxygen to support the combustion. Obviously in a mixture there has to be at least 11% of oxygen, otherwise the combustion will not sustain, right? This is the standard of ISGOT, right? Then we again we go for 12%, 14%, 16%. In that way we go up to 21%. Same for hydrocarbon vapor, that is methanol vapor. Here the cargo is methanol. We go for 10%, then 5%, then 10%, right? In that way 20%, 30%, 36%, 40%, 50%, 60%, 70%, right? So here you can see that we have already marked the lower flammable limit 6% and upper flammable limit 36%, right? These 2 points will help us to draw our flammability diagram, right? Now what you need to do, you need to take a point where after discharging, right? After discharging the methanol, you have got a you have sent your gas monitor, and you have checked the hydrocarbon limit, right? You have seen that the hydrocarbon is 50% over there, right? And you have sent the oxygen analyzer as well, and you have found the oxygen analyzer show that the hydrocarbon oxygen is 16%, right? So the tanked this tank hydrocarbon and oxygen mixture is over there, right? Now we draw that point and we connect that one with 21% of oxygen, because at any time of the during the process, the oxygen percentage cannot be more than 21% unless you insert extra oxygen, but we normally don't do it, right? So this line 21% and that current point for oxygen and hydrocarbon vapor, we just connect that one and we give it a name, we call it an ER line, right? So when there was no hydrocarbon, there should be 21%. Now obviously there is some hydrocarbon, 50% is hydrocarbon of the percent tank volume, and we have already seen that we have got 16% of oxygen of the tank volume, right? And we got a ER line, right? Now on that ER line actually we'll draw the flammability diagram, right? Now what you need to do, we need to draw a line on the lower flammable limit, right? That straight line, lower flammable limit, that indicates our lower flammable limit. Then we'll draw another line on the upper flammable limit, right? That line, we know that upper flammable limit 36%, so we'll draw another line on the upper flammable limit, that is the line, right? And we already know that as per ISGOT, to support combustion we require at least 11% of oxygen, right? So we draw another line over there, right? So we got a shape like that, right? So theoretically, if the oxygen and hydrocarbon mixture is within this area, right, or within this area, then the combustion should sustain, right? And if you press some, if you give some ignition, the combustion should sustain. But industry has found that not all the area supports combustion, right? So instead of having this this rectangle type shape, it actually follows a elliptical path like that, right? So industry say that if your hydrocarbon and oxygen percentage is within that area, then only it will support combustion and it will sustain combustion. Understood? So that area actually we call it as a flammable envelope, right? Above that area we call that area as too rich to support combustion, and below that area we call it too lean to support combustion, right? So that is the process of drawing a flammability diagram for a specific cargo. So you can actually draw the flammability diagram for any cargo in your onboard your ship, and in that way actually you can draw it. Now what you need to do, right? Now we need to see other areas also, right? We have got here below 11% we have got a zone. That zone we call it non-flammable zone, right? Here actually the oxygen and hydrocarbon mixture is in such a percentage that it doesn't support any combustion, right? Then we have got another area here, that area we call it overreach, right? Here the hydrocarbon concentration is too much, that and oxygen concentration is too less, that it doesn't support combustion. And again here we have got another area we call it too lean, right? Here hydrocarbon percent is too less to support the combustion, right? So in that way actually we can draw a flammability diagram for any cargo, right? Now let's assume you have got two tank, right? Maybe one tank can be one port, another tank can be one starboard. Both the tank was having methanol cargo, and you have discharge. After discharging, you send your gas monitor, and you have found that the hydrocarbon percentage and oxygen percentage is on A for maybe one tank 1, and at B in in C in tank 2, right? So here you see For tank 1, we have got a hydrocarbon and oxygen mixture percentage, which is on the tank over here, and here I've got another oxygen and hydrocarbon mixture percentage, which is over here. Now if we open the tank dome, what will happen? The air will get inside the tank, right? So we call it dilution with air, right? Or normally we call it on board ship aeration, right? So if we dilute the tank atmosphere with air, what will happen? The hydrocarbon percentage will go down and oxygen percentage will go up, right? Because on the air we have got automatically the oxygen, right? So at some point when the hydrocarbon percent is going down and oxygen percent is going up, the tank atmosphere will follow that line, AB line, right? The tank atmosphere will follow AB line. So you see this line has got a problem. What is the problem? The problem is that along the path of that line, that AB line, the tank atmosphere passes the flammable envelope, right? That red zone area, right? So that during that time it is the unsafe state of the tank. If there is any ignition, the tank may combust, right? The tank may sustain flame, right, or fire, right? And as a chief officer or as a duty officer, you don't want that. Let us see on the tank 2 what happens in the tank 2. We go to tank 2 and we open the tank dome, and we see that the air is getting inside the tank, and as the air is getting inside, what will happen? The hydrocarbon percentage will go down and oxygen percentage will go up, and the tank atmosphere will follow that path, CB line, right? So we can see that for tank 2 actually the tank atmosphere never passes the flammable envelope. So so if we do aeration or if we do air dilution, there will be no chance that there will be any fire, because it doesn't go within the flammable envelope, right? Now from this picture, let's draw a tangent from B with the edge of this eclipse, and we get a line, right? So this line is called the critical dilution line, right? So this line will separate the safe and unsafe dilution path of gas mixture, right? So that's why this line is called the critical dilution line. So in the tanker, we always want to remain under this critical dilution line. Understood? So therefore the dilution with air initiated about critical dilution line is unsafe, and if we do same thing below the critical dilution line, we call it safe. Now as a chief officer, what to avoid unsafe situation, you need to bring down tank 1 atmosphere from A to C, right? How do you do that? On board ship, we do that one by introducing non-flammable gas, right? Like we sometimes we may introduce nitrogen gas, right? Or other inert gas, right? So this inert gas, actually that gas will not make any kind of reaction, and it will not support combustion, right? So we insert the inert gas, right? Normally we go for the nitrogen gas, or if it is the cargo is not that sophisticated, we can go for the flue gas for carbon dioxide carbon dioxide, right? So we insert the inert gas, and you'll see that. So as we are inserting the inert gas, what will happen? The inert gas will take out the hydrocarbon from the tank, and your hydrocarbon limit will automatically go down from A to C, right? And once it passes the critical dilution line, then actually you are safe, right? So now once it goes to C, then you can dilute the tank atmosphere with air, and it will follow the CV line, and it will be safe then, and you will avoid the risk of passing through the flammable zone during the operation, right? In that way actually we do operation on board tanker. I hope this diagram or this method will help you to understand the flammability diagram better. Let me know if you've got any question or anything. We can discuss more about that. And if you find these lectures useful, please subscribe and share to your friends. Thank you very much. See you in the next lecture.